Greetings, I am Malak Trabelsilov, the founder and managing director of Vernwell Management Consultancies, and it is a space and deep tech focused Dubai-based consultancy firm. And you are watching the DARQ highlights of the week. And let's remember one more time, DARQ stands for a combination of technologies including distributed ledger technology, artificial intelligence, extended reality, and quantum computing. And you will see me often talking about quantum technologies in general. As mentioned in our previous highlights, we are covering a series of videos to highlight some of the security challenges concerning emerging technologies, taking quantum technologies as example. Today's highlight is about quantum technology, identification, and the implication of these technologies on national security. Let's have a brief about various quantum technologies, starting with quantum communications. Using quantum physics principles, quantum communications is based on quantum states of photons and protocols to transmit data securely. These rules allow particles, typically photons, used to transfer data, to enter a state of superposition in which they can concurrently represent various combinations of 1 and 0. From a cybersecurity standpoint, the brilliance of qubits is that if a hacker tries to monitor them in transit, their super fragile quantum state collapses to either 1 or 0. This implies that hacker can't meddle with the qubits without leaving a trail of evidence. Now let's see it from a security and defense standpoint. Quantum communications could enable the safe networking of quantum military sensors, computers, and other devices, boosting performance over a single quantum system or classical communications network. Quantum key distribution, or QKD, is a subset of quantum communications that employ quantum physics principles to encrypt data before sending it via traditional networks. QKD offers secure communications that cannot be intercepted secretly during transmission. However, QKD communications can be intercepted at the relay station now necessary for long-distance transmissions. China invested extensively in QKD and finished the construction of 1,250 miles Beijing-Shanghai quantum network in 2016. The most widely used QKD system employs optical fibers for transmissions over hundreds of kilometers with great stability but significant channel loss. Another significant QKD technique uses satellites and ground stations for transmissions of thousands of kilometers. China deployed the world's first quantum communication satellite in 2016 and accomplished QKD with two ground stations 2,600 kilometers apart. In 2017, a QKD network was constructed using a 2,000 kilometers long optical fiber network between Beijing and Shanghai. For example, Chinese scientists have established the world's first integrated quantum communication network, combining optical fibers on the ground with two ground-to-satellite links to achieve quantum key distribution. In the last year, the team extensively tested and improved the performance of different parts of the integrated network. For instance, with an increased clock rate and more efficient QKD protocol, the satellite-to-ground QKD now has an average key generation rate of 47.8 kilobits per second, which is 40 times higher than the previous rate. The researchers have also pushed the record for ground-based quantum key distribution, QKD, using a new technology called twin-field QKD, TF-QKD. Such an achievement puts China and its allies at a competitive advantage, putting also other nations' national security at risk since it would make their adversaries lose critical information. Quantum communication technologies depend on the collapsing nature of qubits, one thread to make sending and receiving crucial encryption keys possibly unbreachable. In situations like communicating with submarines, these ways can be quite valuable. Quantum communication employs blue-green photons, which may travel far further and deeper in water than radio waves. Now, let's speak about quantum simulation. Quantum simulation employs programmable quantum building blocks to simulate the interactions that underpin a more difficult to access quantum system. Experiment development in this area has been absolutely spectacular, allowing for the isolation of single tiny particles at the nanoscale, manipulation and control of their internal quantum states, and detection with great fidelity. Using 9 superconducting qubits, researchers at Google and the University of California, Santa Barbara, and other universities were able to simulate the intricate energy spectrum predicted for 2D electrons in a magnetic field, the Hofstadter butterfly. How about quantum sensing? Quantum sensing makes use of quantum physics principles within a sensor. According to the Defense Science Board, this is the most advanced military use of quantum technology, and it is presently poised for mission usage. Quantum sensing has the potential to improve a variety of military capabilities. For example, it might give the alternate location, navigation, and timing alternatives, allowing militaries to continue operating at full capacity in GPS degraded or GPS denied circumstances. Quantum sensors have the potential to be employed in intelligence, surveillance, and reconnaissance roles. Successful development and deployment of such sensors might lead to considerable gains in submarine detection, affecting the survival of sea-based nuclear deterrence. Because of their projected sensitivity to environmental fluctuations, quantum sensors might potentially help military personnel locate buried constructions or nuclear stockpiles. The sensitivity of quantum sensors might similarly enable the military to detect electromagnetic emissions, increasing electronic warfare capabilities and perhaps helping in the detection of hidden adversaries' location. And the qualities of the blue-green photons under the so-called quantum light detection and ranging or quantum LIDAR might transform undersea warfare. Currently, sound navigation and ranging or sonar is detecting obstacles and other submarines with accuracy detection through active sonar pings, but it reveals a submarine's whereabouts. Quantum LIDAR is prone to solve the issue and help submarines avoid being detected and tracked. With only few applications, it's difficult to quantify quantum technology's influence on national security. Quantum information science can have a wide range of effects depending on the application and technology. Quantum communications and LIDAR or light detection can make submarines harder to detect, but quantum gravimetry can help discover them. Technologies have both beneficial and harmful effects depending on how they are used. And it is all about who would win the race in harnessing the technology before the others to gain supremacy. And the ultimate race is the race related to quantum computing, which will be discussed in our next highlight of the week. Stay tuned for the next highlight to find out about quantum technology and its security application. Actually, we will speak about quantum computing and its security implications. Meanwhile, contact us for further input and let us assist you in making proactive plans for your quantum technology deployment. Follow us on LinkedIn, Facebook, and Instagram, and do not forget to subscribe to our YouTube channel, Vernwell Official, and like, comment, and share this video. Until next week, may the dark be with you.